We've spent a bit of time talking about polar bonds. If we remember, what makes a bond polar is if one atom that is making a bond is more electronegative than the other. In this case, the more electronegative atom will more strongly attract the two electrons in the bond to itself. So we can think of the more electronegative atom pulling on those electrons more than the less electronegative atom. Let's take a look at a CO carbon-oxygen bond. We know that oxygen is more electronegative than carbon. Therefore, we would draw an arrow in the direction of the oxygen, the more electronegative atom, and put a bar on the side of the less electronegative atom, the carbon. We call this representation the dipole for that bond, but it's just tracking the direction on which the electrons are being pulled within the bond. But what happens if we have a molecule that contains multiple polar bonds? How do we know if the molecule as a whole is polar or is a permanent dipole, or if those polar bonds offset or cancel each other out? Let's draw it out. Take CO2. We have two carbon-oxygen double bonds going in opposite directions. We're AX2 and the central atom has no lone pairs, so that gives us a linear geometry. We know that the carbon-oxygen bonds are polar towards the oxygen, so in all four bonds, the electron density is being pulled away from the carbon towards the oxygens. So since the electron density is being pulled away from the carbon, the molecule should have a permanent dipole away from the carbon, right? Well, no. In this case, the molecule is symmetrical. We have bonds pulling the electron density away from carbon to the same magnitude, but in the opposite direction. Therefore, these dipoles offset each other. Although the bonds themselves are polar, the molecule as a whole is not polar. It's relatively easy to visualize polarity for carbon dioxide because it's linear, and the symmetry is easy to see. If we were to fold carbon dioxide in half, it would be a mirror image of each other, or they would fit on top of each other nicely, like two pieces of bread on a sandwich or a book going from open to closed. But it's not always easy to see the symmetry. So what about a more complicated molecule? Let's take a look at NH3. NH3 has a steric number of 4, but one of those groups is a set of lone pair electrons. The NH bonds are polar towards the nitrogens. But then we have a lone pair of electrons that are also pulling the electron density away from the nitrogen. Because of this, the molecule has a permanent dipole, and the sum of all the dipoles in the molecule is drawn towards the nitrogen and the lone pair of electrons. Another way of thinking about this is that the molecule is not symmetrical due to the presence of the lone pairs. Another way of thinking about this is that this molecule is not symmetrical due to the presence of the lone pairs, and therefore the dipoles of the nitrogen-hydrogen bonds don't cancel each other out. Let's consider carbon tetrafluoride now. Here's the Lewis structure. Let's draw out the tetrahedral version of the molecule. We add in the dipole moments for the bonds, and voila! CF4 contains 4 individual polar carbon-fluorine bonds. These bonds are all pulling the electron density away from carbon. However, this molecule is not polar and does not have a permanent dipole. Why not? The molecule is symmetrical because every bonding group is a single bond to the same atom. The CF bonds have the same dipole and every bond is the same strength. Therefore, to the complete symmetry of the molecule, the dipoles offset each other to give a non-polar molecule. And finally, one last example, CHCl3. When we draw out the molecule, the CCl bonds have dipole moments towards the chlorine, while the CH bond is a dipole towards the carbon. The net dipole of the molecule, therefore, is drawn towards the electronegative chlorine atoms. Is this molecule polar? Yes. Why? It all comes down to the molecule not being symmetrical. All of the bonding groups are not to the same atom. 3 bonds are to the same atom and therefore have the same strength and dipole. However, one of them, the CH bond, is different. Therefore, the dipoles add to each other rather than offsetting each other, and we see a net dipole for the whole molecule towards the chlorine, more electronegative or polar chlorine atoms. Want a quick way to determine if a molecule is polar? Here's a handy diagram. First, does the central atom have any lone pairs? If the answer is yes, then the molecule is polar. If the answer is no, you have one more question to ask. Are the bonding group atoms that your electron groups are connecting the central atom to identical? If your central atom is bound to identical outer atoms, then no, the molecule is nonpolar. If the central atom is bound to different atoms, so all the outer electrons are not identical, then the molecule is polar. So again, if all those atoms that are bound to a central atom are identical, they will have identical dipoles that will cancel each other out. But if we have different atoms that are attached to the central carbon, those dipoles will not cancel each other out, and therefore we will have a polar molecule. Individual examination of these bonds can tell you if the molecule is nonpolar with polar bonds, or nonpolar bonds, or nonpolar but with polar bonds.